Okay, I think we will start now. Right. Assalamualaikum and good evening to everyone. We greatly appreciate all for joining us in the KPPIM International Webinar 2023 on Mathematical Science Section 9. Hashtag Boost Tour Visibility. Your presence is our happiness. My name is Noratika Nordin and I am the moderator for today. Before we start, let's recite Surah Al-Fatiha. Right? We are back together in the night sessions. Alhamdulillah. Thank you very much for joining us again. Before we begin, we sincerely hope that all participants will fill in the attendance form to get your e-certificate. The attendance link will be given at the end of this sessions. All right, please allow me to welcome Mr. Asadov Quvonchbek Urinovich, the first speaker for our night session. Mr. Quvonchbek has served as senior lecturer at the University of Management and Future Technologies, Tashkent, Uzbekistan. He is also a PhD student at Tashkent University of Information Technologies, named after Muhammad Al-Khwarizmi. His area interest is dynamic system. Welcome. Mr. Quvonchbek will speak for 30 minutes on his research topic, modeling reflectionless transmissions of the bright soliton solutions of the nonlinear Klein-Gordon equation, followed by a 10-minute question and answer session. Big applause to our speaker.
Okay, thanks. Assalamu alaikum and good day, dear participants of KPPIM International Webinar 2023 on mathematical science, and happy Juma for everybody. I am Quvonchbek Asadov, senior teacher of University of Management and Future Technologies. Today I want to show presentation on topic on the theme modeling reflectionless transmission of the bright soliton solution of the nonlinear Klein-Gordon equation. So outline my presentation is consists like these parts. So abstract, in abstract, you can see in this presentation we consider modeling reflectionless transmission of the bright soliton solution of the nonlinear Klein-Gordon equation on the metric star graphs with 3 semi-infinite bonds. At the branch point, we put two types of vertex boundary conditions. The wave continuity and the condition for derivatives of the wave functions as a generalized Kirchhoff rule. We solve this equation satisfying vertex boundary conditions from which the energy and momentum are conserved. We also show reflectionless propagation of the bright soliton solution by several different schemes. Plot the reflectionless coefficient and extend to other topologies. So we show that considered bright soliton solution is satisfying vertex boundary conditions to be unstable. So introduction, the nonlinear dynamic of solitary waves that occur in many scientific areas can be described by nonlinear partial differential equations. The nonlinear Klein-Gordon equation is one of the important classes of partial differential equation and is used to model many different phenomena, including the propagation of dislocations in crystals and the behavior of elementary particles. The exact numerical solution, Soliton solution of the Klein-Gardner equation are given in the Pinang work above. In that numerical is solved with the various time and coordinate steps. Found the discretization scheme using Taylor series. The energy and momentum conservating schemes used to integrate to nonlinear Klein-Gardner equation and invariant conserving finite difference algorithms are given 6th lecture. The nonlinear partial differential equation on the branched structures are attached to the most interest in the last decade years. Such attention was caused by the possibility for obtaining Soliton solution of the nonlinear partial differential equation, such as nonlinear Schrödinger, direct equations, and its numerous applications in different branches of physics. The branched structures can be modeled metric graphs. Metric graphs consist of two sets: the set of points and the set of intervals that connect vertices. Topology of graphs can be given so-called a density matrix, where C capital Ij to equal to 1 if Ij are connected, 0 otherwise. Ej is defined vertices. So, problem definition. We consider a star graph with three bonds Ej, from which a coordinate xj is assigned, choosing the origin of coordinates at the vertex 0. For bond E1, we put x1, which belong from minus infinity till the null, and for E2 and 3, we fix x2 and 3, which belongs is from 0 to till plus infinity. In that follows, we use the shorthand notation qjx for qjxj, where x is coordinate on the bond j to which the component qj refers. Klein-Gardner equation on each bonds aj of the star graphs is written as like the first equation. Now we define the vertex boundary conditions at the branched points of the star graphs. Therefore, we derive these boundary conditions from conservation laws. One of the conservation laws is energy defined as like that, second equation, where E capital J equal to this expression, like a third equation. From total energy to equal, we can get the following nonlinear boundary conditions as fourth equations. We need two types of boundary conditions to find a solution of first equation and to fulfill the nonlinear vertex boundary conditions fourth. And therefore, we first type of vertex boundary conditions is the following weight continuity as like a 5 equations. The second type of vertex boundary conditions is given and derivatives of the wave function at the branch points as Kirchhoff rule, like this 6 equations. So objective is more new results are studied in 14th, 18th literatures references, such as a stability of standing wave, small amplitude of Blader's solution on metric graphs, etc. In this work, we focus on one of the exact solution and transmission of the Bragg solution of the nonlinear Klein-Gardner equation through the vertices of the networks. The present work is organized as follows. In the section problem definition, we the nonlinear Klein-Gardner equation on the metric star graph with derivations, the vertex boundary conditions is obtained. In the next section, the Bright-Soliton solution of the formulated problem with the sum rule for the reflectionless transmission in the is analytically given. The momentum conservation law is show constant and plotted the energy conservation law with the plotting reflections coefficient as ratio of momentums. The section before the last one is devoted for the MATLAB analysis of several type of differential schemes to reflectionless transmission. In the last section, the conclusion are given. So, methodology and results. The Bright-Soliton solution of the Klein-Gardner equation on the star graph with 3 bonds. The Bright-Soliton solution of Klein-Gardner equation on the each bond Ej of the metric star graph is the following equation, like a 7th, where L is the initial center of mass of soliton. Fulfilling the vertex boundary conditions 5 and 6, we can get the following constraints, like a 8th and 9th equations. From equations 9th and 8th and 9th, we obtain the following sum rule for nonlinearities, like a 10th equation. Using the Bragg-Soliton solution of Klein-Gardner equation with the sum rule for the nonlinearities, we can also show that another conservation law, that is, the momentum is conserved. So the momentum is constant, but this solution is very unstable. We can check and confirm this fact through numerical analysis. Numerical analysis of Bright-Soliton solution of Klein-Gardner equation on MATLAB program package using the technologies of modern scientific and innovative MATLAB. In this work, we use the solution of the nonlinear Klein-Gardner equation on the metric star graphs with the search for semi-infinite bonds and the problem of reflectionless transmission through these graphs uses the MATLAB. We use several kinds of differential scheme to solve this problem. Exactly, we 4 scheme is checked, and every time this Soliton solution was not stable. One of them, the numerical Soliton solution by Taylor series, represented follow commands of MATLAB. There is V1, V2, V3 defined vertices. At the branching point, we impose 2 types of boundary conditions, weight continuity and the generalized Kirchhoff rule for the derivatives of the wave functions. We obtain a graphical model for solving this equation that satisfies the boundary conditions and the laws of conservation of the energy and momentum at the nodal point. We also show a graphical model of the propagation of the Bragg solution and calculates the reflection coefficient and total energy. There is E1, E2, E3 is energies depend every bonds, and the EM is the total energy. Thus, we simulate the reflectionless transition of the exact Bragg-Soliton solution of the nonlinear Klein-Gordon equation through the branched points. The figure 2 we show reflectionless transmission at the momentum. The first one is t equal to 0. It's beginning. And the second one is t equal to 5, and the end t equal to 10. So from here, it can be seen that the numerical analysis of the soliton solution graph of the solution function collapses in the transition, and clearly this solution is not stable in this regard. In the figure 2, we can see its reflectionless transmission isn't stable at the momentum of t to equal 0, 5, and 10. There are also, I show another kind of differential schemes which calculated. There are red circle, I defined it. There is its transition is collapses, and there is also. So in the figure 3 is it is plotted the energies on the each bonds and the total energy. From this figure, it is clear seen that the total energy is constant. This systematic analysis clearly illustrates the necessity for reflectionless to be absent at B3 to equal to 3 here. So conclusion. In this work, we studied the nonlinear Klein-Gordon equation on the simplest metric graphs and the star graph with 3 semi-infinite bonds of 3 graphs. First of all, we derived the nonlinear boundary condition from the energy conservation law. Satisfying these boundary conditions at the vertex, we obtained the weight continuity and the condition for derivatives of the wave function as Kirchhoff rule. We obtained the bright soliton solution on the metric star graph and the constraint as inverses of nonlinearities for the reflectionless transmission by several kind of differential schemes. So in the figure 2 show it isn't not stable. Using the bright soliton solution, we got that the total momentum is conserved. We show the conservation of the total energy and calculated the reflection coefficient as a ratio of the momentum on the first bond to the total momentum in the figure 3, respectively. So recommendation for future work in future directions. From that, we also can extended obtained results as the formulation problem and constraints for the nonlinearities to other type of graphs. For future, we thread that the King's soliton solution for this kind of problems. Thank you for attention. Any question? If
Okay, all right. Thank you for your sharing, Mr. Quvonchbek. Right, so now we will open our question and answer session. Okay, so we have one question at the chat room. So the question is, may I know in which field of real life this work can be applied? It is, this is more to the chemical reaction. Mr. Quvonchbek, this is the question.
My research area is transmission of the reflection as transmission of the nonlinear Klein-Gardner equations, meter star graphs is applied to transmission of informations sets, networking, any kind of sets, communication sets.
Okay. And is this more to the chemical reaction?
What?
This is more to the chemical reaction?
Communication?
Sorry, maybe I want to describe my question. The reason in that is like just like a chemical reaction because I see the word of bonding and energy, so I relate to the chemical reaction that I was studied before in my.
No. It's not chemical reaction. Okay, I understand. It's not for the chemical reaction. It's a physical direction. It's a physical process.
Okay, thank you.
Okay. There's any other question? Anyone want to ask any question to Mr. Quvonchbek?
I have a question. Mr. Quvonchbek, other than MATLAB software, is there any mathematical software that can be used, either maybe Maple or Python? Do you have any idea? Any alternate application software that can be used to have this kind of graph?
Yes, we can use any kind of applications like Mathematica or Matcat maybe or program languages, some kind of. But MATLAB is very easy. No, maybe it's for easy to solve this kind of problem to mathematics, which understood mathematics.
Because I'm familiar with Mathematica, so I think MATLAB's coding is quite difficult to understand rather than Mathematica. So
Yes.
that's what I'm saying is if Mathematica can do this kind of problem.
Yes, there is maybe some kind of difference which Mathematica maybe is easily you can use MATLAB maybe difficult to understand, solve some equations, solutions maybe. But illustration, I think illustration, graphical illustration, I mean, it's too easy on MATLAB. For that reason, now we use this program package.
Okay, thank you.
All right, so there's any other question?
There's one question from me, I think from the text. I just read it. Just want to know the model solution that you obtain. Is it by a closed form solution or is it by approximated solution?
It's the exact solution.
Exact solution.
Exact solution, yes, of
Oh.
Klein-Gordon equation. One of solution, exact solution is. There are several Soliton solutions of Klein-Gordon equation. We just research bright Soliton solution. It's the exact solution.
Okay, thank you, thank you.
Okay, thank you. There's any other question from other participants? I think I just have one question. It's very simple. I just wonder, is it exist of linear Klein-Gordon equation, Mr. Quvonchbek?
I don't understand. Excuse me.
Since you do non-linear Klein-Gordon equation, is there exist a linear Klein-Gordon equation?
No, it's not linear.
Or it's for non-linear only?
It's non-linear, but the form of linear Klein-Gordon equation also execute.
Mm.
It's not non-linear Klein-Gordon equation
Okay. All right.
because
So-
it's non. Is my research area learns non-linear systems.
Ah. Okay. Thank you for that. Any other question for other participants? No? Okay, I think there's no question from others. Okay, so thank you, Mr. Quvonchbek. Now I will introduce our second speaker.
Thank you.
Okay, thank you, Mr. Quvonchbek.
Thank you for all.
All right.
And good luck for research area. God bless you.
Okay, thank you, Mr. Quvonchbek. Okay,
Thank
so now I will introduce our second speaker. Okay, our second speaker can start share the slideshow. Okay, so right. So our second speaker of this session is Teknologi Syahrul Fithry bin Senin. Teknologi Syahrul Fithry started his career as an academician at UiTM Cawangan Pulau Pinang in 2004. A graduate of the Universiti Malaya, he was actually involved in structural and civil engineering consultancy work in the year of 1997. Currently, he is actively involved in using MATLAB and GNU Octave for his numerical method related research works and lectures. His focus area of research are on structural damage or structural defect assessments data from building inspections work by the radar signals from electromagnetic wave sensors such as ground penetrating radar and other related sensors. Teknologi Syahrul Fithry also has been recognized as a professional technologist in the building and construction field since 2020 and an active speaker with the institutions of engineers. Welcome. Technologist Syahrul Fithry will speak for 30 minutes on his research topic, which is the usage of ground penetrating radar GPR on the reinforced concrete structure investigation, the applications of mathematics for human safety. Next, followed by a 10-minute question and answer session. Big applause to our second speaker. Sorry, it's Cik Syahrul. I cannot hear. Maybe you mute. Can you try?
Yeah, I have unmuted.
Okay,
Okay, sorry.
okay.
Read it again.
All right.
Okay, sorry. Okay, Assalamualaikum warahmatullahi wabarakatuh. So can you hear my voice?
Yes, clear.
Okay, good. Okay, Assalamualaikum warahmatullahi wabarakatuh and very good evening to all of the participants, especially to our moderator, Cik or maybe Puan Noortika Nordin, and fellows of our presenters and also our friends. Okay, today my presentation is more not on the research part, but more on the knowledge sharing of one technique that currently now getting interest from the engineering communities, which is by using an equipment that we call as a ground penetrating radar. Okay, and this equipment has been used in line with the IR version 4.0, the new technology, to perform structural investigation. So when I said about structural investigation, meaning that it is more on the buildings, bridges, dam, bitumens, and so on, the structure that you have used on your left, and we want to investigate whether it is safe or not to be used throughout of its lifespan. Okay, so this is my name, Syahrul bin Senin. I'm from Center of Civil Engineering Studies in the UITM Pulau Pinang, in the campus of Permatang, Pulau. So approximately this is my presentation content. We will start with some introduction part, why we do this webinar. And then after that, we straight away to the problem that you want to investigate, which is the concrete. So why I'm choosing concrete? Because most of our structures in Malaysia is made from concrete, very less made from steel. So that's why I'm focusing on the concrete. And after that, I will do the structural inspection on concrete by using this GPR, ground penetrating radar. Okay, why we have to know all of this? Because structures also like us a human being. Okay, why? As I said before, because if you, let's say, go to the hospital when you have some illness, so you will show your symptom to the doctor, and the doctor will ask you about this question. So what is your problem? So then you can say to the doctor that I have some headaches, I have some fever, I have cough, and so on. So the doctor can analyze that. Doctor can analyze that and also give you some kind of treatment to ensure that that kind of problem can be alleviated. But the problem is that when you have structures like this, okay, there is an engineer inspecting the structures, okay, and I don't think you can ask the structure something like this to ask what is the problem. So as an engineer, you must understand the symptom that is existed in the structure, so that the engineer can investigate and perform what kind of treatment to be done. Okay, can I answer phone name? Wait. Hello. Hello. Hello ya. Ya, saya tengah ada webinar lah. Nanti call balik boleh tak? Saya tengah webinar, Encik. Saya tengah webinar, Encik. Nanti saya call Encik balik. tak apa. Okay, sorry for the interruption. Okay. Okay, so this is some of the problem that can be exist in our reinforced concrete, and this is very, very critical. As you can see that some of the structures having the cracks, okay, and you have also corrosion. This is underneath of the bridges. So I don't think you want to have your structure to be in this condition and you want to treat. So the best idea is to treat before this thing appears, and we do some kind of treatment before the critical stage of this to be happen. So this is already critical. So we don't want this to be happen. Should be we treat before it happen. So why we need to know that situation, because we want to prevent a lot of maintenance. Because maintenance will deal with a lot of costs to repair. Because we have to prepare the materials, the treatment, and so on. That will be involving money and time. We have also to evaluate the structural integrity and also safety. Because for any users, they have to know that whether the structure they are using is safe or not. Because this is the aim of using the structures. So no one will use a bridge that is already like to be deflected, because they will afraid about the integrity and the safety. So that's why we have to know this by using a new technology. Okay, and that's why we want to know the health of that structure by using this equipment that we call as ground penetrating radar.
Beş altıda sağ verirdi.
Okay, can you hear my voice? Hello? Hello?
Clear?
Can you hear my voice?
Yes.
Okay,
Clear.
sorry. Because I know you cannot hear my voice. Okay, so this is the equipment that, as I said before, we have this kind of system, whether to be a wheel cut like that. The first picture on the left is the wheel cut, where you can push that equipment forward, and there is a scanner at the bottom there. You can see a red box there. There is an antenna that will scan the beneath of that surface. Another one is on the most right side, where you have a very small one. This is we call it as a hand cut that you can scan on the surface of the concrete, such as like slab, floor slabs, column, and so on. So this is much more practical, they say, on the building part, on the most right. And the left part is more on the, let's say, for soil investigation. So this is the same picture for the small part, and I want to talk more on this one rather than the left part picture, which is using for the soil, which is the hand cut system. So you can see here, there is a man here that tried to push this GPR, where this GPR have its built antenna, where the antenna will emit certain kind of electromagnetic wave through the concrete, and it will scan like a doctor scanning the stomach of, let's say, of your wife that that is waiting for a birth. So just like that, you can see the picture. So this is the main component of that element, which is you have the computer. So any GPR must have this CPU unit, because this CPU unit will try to control the equipment to emit the radio magnetic waves. And this is the cable that will connect the CPU to the antenna. Okay. And so why we need GPR? Because for any engineering works, you need a very fast investigation. Imagine if, let's say, you want to perform investigation on a bridge, and a lot of cars is using that bridge. So in order to make sure that you can investigate that bridge much more faster, it is recommended to use GPR, because you just scan on the surface of that bridge. Maybe within 30 minutes, you already scan the whole bridge without to do any damaging to the structures and obstruction to the road users. So that's why GPR is most commonly used now for structure investigation, and that because of this rapid data collections. And the data that you can have is a very, very good because highest resolution, you can see the picture much more better. And there is no need to do some kind of damage because other kind of method will have to damage the structure. So if let's say you want to investigate a bridge, you need to perform like a drilling, and you have to drill from the top of the surface of the concrete to the bottom by using a certain kind of equipment, and that will damage the structure. So by using this, you don't perform any damaging at all, and that's why it's very, very useful. Okay, the principle of that GPR can be shown by this video. So hopefully you can hear this video.
Hi, my name is Kevin. Today I'm going to show you how to use GPR for both rebar and conduit location in concrete. So a very real situation you can run into in a normal job. After turning the unit on, we're again ready to collect some data. After moving the Mini over top of my concrete slab, I see here we have some different colored bumps on the screen now. Using a combination of the vertical line and the laser, I know where my unit is, and we see it's lined up perfectly with our piece of reinforcement. And this is shown to us by the white bump on the screen. But after backing up and lining it up with this black bump, we see here that it's lined up perfectly with our piece of conduit.
Okay, so if you see carefully, can you see that that concrete section is embedded with certain kind of features, the voids. So by using this GPR, you can detect that embedded voids by these pipes just by moving that GPR on the top of it, and you can see some kind of images performed on the screen. So without any damaging of the surface, you can get the image inside the structure. So this is a very useful feature. And if let's say you want to scan how many steel inside the concrete, then you can perform that measurement. So this is very useful if let's say you have a new building, okay, and then you want to upgrade the usage of that floor. So maybe the current usage of the floor maybe for garage, but after certain years you want to use for the floor for heavy usage of application. So maybe you want to know what are the construction inside the floor. So by using this equipment, you can investigate how many steel inside, what are the spacing of the steel inside, how deep is the rebar, and so on, so that the engineer can design a future requirement for the new application. So this is a very useful also if let's say the structure doesn't have any plan anymore. So maybe the structure plan has been missing by the contractors or by the developers. So you don't have to find that drawing. You can draw that drawing on your own just by using this equipment. So it's a very, very useful features if you use this equipment for your work. So this is the principle of using that GPR. As I said before, the GPR will have two transmitter, the receiver and transmitter, where the transmitter will propagate certain electromagnetic wave through that material. So let's say if the material is a concrete, so meaning through the concrete, and let's say when the wave hit some kind of object, so maybe the object can be a steel, can be voids, can be the bottom surface of that floor. So the wave will be reflected back, okay, and the receiver antenna will interpret that signal, and it will be processed by the CPU, and you get some kind of images, as you can see on the top of the screen of the GPR. So these images will have to be interpreted by the expert in order to predict what will be the possible depth, the possible length of that object that is embedded inside the concrete structures. Okay. So if let's say you have a steel inside the concrete like this, so when you put your GPR along on the top of that concrete, then you have an image like this where you have a reflection like this. So this reflection will give you the position of that rebar. So the engineers can estimate where is the position of rebar just by interpreting the generated images on the GPR. And so if let's say you are scanning a concrete section, okay, this is the concrete section. You put on the top of that image by a GPR. So once you push the GPR from the left side until to the right side, then you can see this kind of images. And you can see that the inverted U. You can see that how many inverted U here? 1, 2, 3, 4. So meaning that there are 4 internal features that is embedded inside the concrete. So you can see that each of that features will have its own depth from the top of the concrete. So the engineers can estimate what are the depth of that features that is embedded inside the concrete. And if let's say the depth is not correct, so maybe they have to drill that position and they have to correct that rebar position with some kind of preparations. So this is the structure that I said before. This is a floor where inside of the concrete floor you have a lot of rebar or steel that is placed in this manner. So by using that equipment, we can locate and also compute where are the exact position of this rebar. So why we have to know this rebar depth and also position? Because if you don't know the position of that rebar, then we cannot understand what is the maximum load that you can apply on this floor before it's filled. So remember that each floor that you are sitting now is a combination of steel and concrete that has been designed properly based on the calculations. So that rebar position must be put according to the preparation of the plan by the engineers. So if you found that the rebar position is not correct, then we worried about the safety about the structures. So that's why we have to know what is the current construction features inside the slab without to damage the slab by using the GPR. Okay. So this is another picture showing you the cross section of that slab where you have four number of rebar, 4 number of steel. So you may see that the first steel on the left side, the second steel, the third steel, and the fourth steel. And so by using this picture again, you can determine what is the distance between one steel to the another steel. And we can compare and we can calculate what is the maximum load can be taken by this floor before it's filled. And if you see carefully, there is a what you call this? This a line. Can you see that there is a line at the bottom here, somewhere at the depth of 0.22 here? So this line is the bottom surface of your slab. So meaning that this slab, the thickness is about 220 millimeter. Sorry, 0.22 meter. So we can get another information such as the floor thickness as well as the rebar position. So this is only can be done by using GPR without to do any damaging effect to the structure. And if let's say you are in doubt, as I said, you can perform some kind of coring where you have to dig some kind of holes. You can see that there is a picture here showing you a holes where you have to core by using a certain equipment, and we can take out that core and we can see what is the feature inside the concrete, and we compare with the result from GPR to validate the results. So usually on one construction, we just only one coring only is enough because coring also is a cost. So too many coring, meaning you have to bear with a lot of cost. So by combining GPR and one coring, it is more than enough to validate the results. So we have two measurements to be done. One is by GPR, another one is by coring to validate the result, whether it's correct or not. So this is another thing that we can do also by GPR. We can also investigate whether the steel is corroded or not. Okay, so can you see that the healthy rebar or the healthy steel, the brightness of the inverted U is very bright. Whereas if you can see that the last reflection on the most right, the brightness, the feature is very, very mild. So meaning that there is a possibility, there is a corrosion process has been taken there. So remember that we don't allow any rebar to be corroded in the concrete, because when it is corroded, then there is a possibility of cracks. So by using this equipment, we can allocate which one of the rebar is not healthy, and where one of the rebar is healthy. And you can see that again, the depth of this slab is about 2.5 meter. Sorry, 2.5 meter. It's quite deep. Okay. So this is another picture showing you on the left side the rebar which is healthy, and on the right side where the rebar is not healthy. You can see that the signal is not so clear, mild. So we can identify where is the area that you need certain treatment to the rebar, so that we can replace the corroded rebar with more healthier one which is not corroded. Because corroded rebar meaning that the slab is not healthy. We are afraid about the cracks that will happen in to the concrete later on. So these are the two factors that we will use to know whether our features is healthy or not, by studying the dielectric constant of that material and the conductivity. So these two features is depending a lot on the material properties. So in my case, I'm using concrete as the material. So if let's say our concrete is subjected to water, so meaning that you have a rainy season where the rain can moisture the surface of the concrete. So on that time, the material will be have a high dielectric constant and more conductive. So on that day, you are not advised to use GPR to investigate. Why? Because the signal will be absorbed by that rain, by the moisture, and when a lot of the signal has been absorbed, most of the signal cannot be seen. So that's why there is a limitation for the usage of this equipment, where you have to find the non-rainy season to perform the investigation. So that is one of the limitation of this equipment. Even though it's a very fast, it's very good in terms of costing, but it is very, very sensitive to water resistance. Okay, so this is some notes about the dielectric properties. I don't think I have to explain about it, because I think some of you knows about dielectric properties. Can vary from 1 until 81, and if let's say if you calculate the dielectric properties of water, the value is 81, the highest one. But for concrete, because concrete cannot absorb 100% water, because maximally concrete only can absorb 10%. So when the concrete is saturated in water, the dielectric values will be about 15 or 12. So if for a very dry concrete, it's about 5 to 6, the dielectric properties. So you can see that a very different value of dielectric properties. So that's why we have to avoid rainy season, because it will give you a very unwanted result if you allow water to be combined with the concrete. And will control the reflection strength. Because reflection strength of that GPR is depending on the dielectric properties of that material that is involved in the investigation. eh. Okay, so the same thing also, if let's say if you have a concrete structures that is submerged in the salt water, let's say for JT structures, so the salt inside the seawater can give can increase the conductivity of the concrete, and that also will make the GPR signal to be lost. So meaning that we have to also to avoid or to wait the seawater to be in the low tide, and after that we can perform the investigation. So there are some restriction when you want to use this equipment. And as I said before, the equipment is very subjective, very subjected to this conductivity and also to the dielectric properties. And that's why also for usage of application, we have to select the frequency of the antenna. So for concrete application, usually the depth of the structure investigation is not more than commonly less than 1 meter. So when you want to investigate the depth of the structure less than 1 meter, then you have to use a very high frequency antenna, such as 2000 megahertz. But if let's say you want to use GPR for soil investigation, so for geological application, where the depth may be more than 10 meters, then you have to use a very low frequency antenna, maybe 800 megahertz or maybe 500 megahertz, because the depth of the investigation much more deeper. If you remember that if you use your radio station, you are using a very low frequency. So why you are using low frequency? Because the signal can be transferred from one place to another place at higher distance. So the same concept applies here. For a very high depth, you have to use a low frequency. For a very shallow depth, you have to use higher frequency. So meaning that you have to choose appropriate antenna frequency in order to perform the investigation. Okay, so as I said before, the same idea that have been talked before, low frequency is useful for deeper depth and for larger targets. And so because this equipment is radiating electromagnetic wave, so there is also another limitation, is that we don't allow any other equipment with a similar frequency to be active together. So meaning that when I use this equipment, I have to switch off my phones, my mobile phone, because my mobile phone also can radiate certain electromagnetic energy, and that will be also a problem, because it will create artificial signal that can be misleading signal to the GPR. So this is one of another limitation. Okay, this is my last slide, where I want to show you the future usage of GPR. So hopefully you can enjoy this about 2 minutes video. Okay, thank you. And I pass back to our moderator. Thank you.
All right, thank you very much for sharing Technology Syahrul Fithry. So now we will begin the question and answer session. So if other participants want to ask question, you may ask. Okay, is it any question? Very good sharing. Technology Syahrul Fithry.
Take some questions.
Mr. Quvonchbek have
Yeah, Mr.
question.
Quvonchbek.
Okay, it was very interesting presentation. But my question is, what depend on the mathematical science? It's GPR, your GPR system, or your this research? How to depend to mathematical?
Can you again repeat the question? I didn't clearly hear.
How to depend to the mathematical science your this work?
Okay. So the principle behind it is more on the electromagnetic wave reflections. Okay, and the reflections of that GPR is really depending on the directional properties of that material that is propagated by that electromagnetic wave. So if let's say you are investigating a concrete section, so you will put that GPR on the top of the concrete. So remember that between your GPR and your concrete, there will be a very thin layer of air, a very, very thin, before reaching the concrete. So air have different dielectric properties compared to the concrete. Air, the dielectric property is about 1, whereas dry concrete is about 5 or 6. So when the wave propagate from that thin air to the concrete, then there will be a reflections. By using that reflection, that is reflected by the surface and go back to the antenna, it will be interpreted to calculate what is the depth. So if you do the pre-processing in nature, because I didn't show you the pre-processing of the data, you can even calculate how thin that air layer until to nanometer level. But in this case, I didn't show it to you lah. I just show it inside the concrete only. So if let's say after the wave propagating to the concrete and now hit with the steel. So remember that steel have a very different dielectric properties than the concrete. So the wave again will be reflected, and some of the wave will be go deeper. So that reflection will also be interpreted as another feature detected by this equipment, and the time difference from the surface of the concrete to the steel will be also computed. Not only the depth, but also we can also get also the location of that rebar. So the basic science principle behind it is more on the reflections of wave, electromagnetic wave, and the impedance. The impedance in this case will be the dielectric properties. In fact, the concrete is not only having dielectric properties to reflect the wave, it has also the magnetic properties and also conductivity. But in theory and from a lot of experiments, these two parameters can be neglected because the effect is very small. Because usually in concrete, the amount of magnet material is very rare, unless you have a mineral that have hematite and so on, isn't it? And
Okay.
conductivity is also quite small, unless the concrete is immersed by salt water or rainwater. As I said, that you have to avoid when you do when you use GPR measurement. So that is more or less about the concept or the mathematics behind this equipment. Hopefully, I answered some of your questions, maybe.
Okay. I just asked, did you use some kind of mathematical model on your research?
Yeah, yeah.
On your work?
In fact, I have created that mathematical model. If you see my my background, that is the paper.
Okay.
One paper that showing two mathematical model that I have developed during my work by using this equipment.
Okay.
There are existing models, such as they are trying to modify the Snell law, because electromagnetic is like just like a light, isn't it? With certain spectrum of energy, isn't it? So idea has been used a lot in this GPR, but in my work, I modify that theory and I create my own model.
Okay.
Yes,
Okay. Thanks.
no problem.
Okay, is there any question from other participants?
Hi, good morning. Good evening.
Good evening, no
Actually, I
problem.
have a question, sir.
Yeah, boleh.
I'm wondering, is the GPR suitable only for smooth surfaces or only for flooring structures?
Okay. In actual, okay, in engineering, because our structures can vary from small spot until to largest area. Because engineering, isn't it? Just like civil engineering, you always use bridges, isn't it? You always use bitumen by your car. You use your house. So any areas can be investigated by GPR. That's why we have a lot of models. We have a wheel cut, which is basically good for a large area, and we have a handheld cut that you see picture before that you can use only your hand for small areas. So the manufacturer also play smart lah, because they also want to have money from the client, isn't it? So that's why they have to create for all application, because they will get money from that equipment selling, isn't it? So in actual, any areas where the small or large can be covered. The only that is you have money.
Yes.
Yeah,
Depends.
that is the problem. Money.
All right, thank you, sir.
Okay, no problem.
Okay. All right, so any other question?
In,
Okay,
in actual, okay. Siapa nak tanya? Boleh.
okay, Mr. Syahrul, I heard that your GPR have a limitation for rainy season, right?
Ya, betul.
Is there any way to overcome or that limitation, or it will be another project for it?
That is the problem for the time being, and this is still being under research. How to overcome that problem? Just as Astro, lah, isn't it? When
Yes.
you can watch any television by using Astro, isn't it? So the same thing. So the best way for the time being, we have to live with it, meaning that we have to wait. We have to depend on the forecast weather prediction lah. So we have to know the season of that time when we want to do the investigation. So if let's say they have a rainy season, then we have to postpone that work. So that will be a bad thing. So we cannot do much on that unless you can cover that space by using a very large umbrella. They want to perform the investigation. That only the way that you can do lah. But it's not practical to do that in actual.
Okay.
So that is a challenge lah in civil engineering. So that's why sometimes if you cannot do that investigation, we try to replace with a damaging solution. Damaging meaning that you have to core. You have to drill. If let's say the client chase the time for getting the result, you have to do like that. You have to use that solution. You have to do another procedure, not using GPR anymore. But GPR, the best part of GPR is you can cover a very large space within a very small time. Just like if let's say you are using this method to Jabatan Pulau Pinang Bridge, it's about 2 days only, one stretch from from one end to another end is only 2 days. Very fast. If you use normal way, I think take months. Take months. That is the best part of GPR lah. Provided not raining. that is the problem.
Okay, understood. Okay, thank
Yeah.
you.
All right. Thank you. Okay, is there any other question? So very interesting topic from Syahrul.
In fact, if you have money and you learn this equipment, you can be a consultant. It's very easy to be consultant. If you don't have to buy, you just only rent. You have some knowledge. You can use this equipment for a lot of contractor because now engineers learn how to build building, but engineers not learn how to maintain the building. That is the new prospect of money that you can get from this technology. In university, we learn how to build, but we don't learn how to maintain. That maintenance, if you can cover, then you can get a lot of money. Because this is a part of the maintenance. So for those who want to pension earlier, you can do this job lah.
Okay. All right, I think there's no other question.
Hello, sir. I have
Yeah,
one question.
No problem. Proceed.
Okay, when is the best time to use the GPR to monitor the cement, concrete, flooring structures?
Oh, when is the best time? Okay, as I said, because the limitation of GPR cannot use under watery condition. So when you mix your cement, for sure you will use water, isn't it? So after the concrete has hardened about 28 days, and after you feel that after another 1 month, so usually after 2 months or 3 months, then you can start to use GPR. Because remember, when you mix your cement, theoretically by 28 days it will be hardened for sure, but you still have water inside the concrete. So we afraid that water will affect the results. So in order to make more ideal, usually we allow it until 3 months. And after that, then you can monitor the cement quality by using that GPR. That is the best way lah. Because concrete is very, very, GPR is very, very sensitive to water. And that's why also this equipment has been used in agricultural to find the source of water inside soil. So you can use it for another application for water finding in agricultural. So the application is very vast, not only in the civil engineering, but also in another areas in nature. So if you see the last video, they try to use, they combine the GPR plus drone for covering large areas to find the water pipes, the leak water pipes. Because, and also they use also for finding water source inside large area of agriculture. So hopefully I answered your question.
Okay, thank you, sir.
Okay, no problem.
Okay. All right. So I think that's it. Okay. Thank you, Mr. Syahrul Fithry. Okay. Now, let's go to our photo sessions. I sincerely hope that everyone will turn on their camera for this.
Okay.
Okay. So please look at the camera.
Just a moment.
Just okay. So please open your camera. You're ready.
Yeah.
All right. Okay, so please look at the camera and give us thumbs up and smile. Okay. All right. Okay, thank you very much.
Thank you.
Okay, so dear participants, please kindly fill in the attendance form to get your e-certificate training hours. Purpose for UITM staff. Okay, I will share the link.
Okay, thanks.
This is for UITM staff. You can scan and fill in the attendance form.
Okay. Can you send by email also?
Sorry, Mr. Quvonchbek?
Can you send by email? Email it's also?
This one is for UITM staff for training hours.
Okay.
Okay.
And photo sessions also.
Oh, photo session. Yes, yes, sure, sure.
Okay, thanks.
All right, thank you. Okay, so the night session is now complete. We sincerely appreciate your presence, and we also want to express our gratitude to our speakers for sharing their insightful information. Join us again and be inspired to learn more. Please feel free to contact both speakers via their emails for further collaboration. Before we wrap up the session, allow me to share with you a quotation from American printer and publisher Benjamin Franklin, who was an author, scientist, inventor, and diplomat. Tell me and I forget, teach me and I may remember, involve me and I learn. Till we'll meet again for the next session. Assalamualaikum.
Wa alaikum assalam.
All right.
Thank you.